Hello everyone, I'm Yatin, and just a couple of years ago I was on the other side of the table, and I just hope that today I'm able to do justice when I'm on this side. Currently, I'm working as a research scientist with IBM Research. So this is our team in Gurgaon. So we focus on conversational AI and various aspects of making LLMs useful for our clients, right? So you will hear from three of us, from me, from Gaurav, and from Dinesh in this lecture series. And Dinesh is our manager here, and Sachin is the senior manager. Okay, so let's get started. So in the last couple of lectures, you have been focusing on transformer-based architectures and the LLM race that it started, right? So one crucial paradigm shift that happened in NLP with transformer-based architecture is that of pre-training and fine-tuning. That is, earlier you would take a model, train it for a specific task from scratch, right, and then use it for that specific task. Now, on the other hand, what we have is that we have huge models which are trained by big corporates and big groups. We can't even think of pre-training them with the resources that we have in an educational institute, right? But then once we have it, we have various fine-tuning techniques to use it for the specific task that we have. There are various parameter efficient fine-tuning techniques, right, which makes it possible for us even to use it in a low resource setup, right? So this paradigm already existed in computer vision, right? So in computer vision, we had VGGNet or ResNet, which were trained on a huge ImageNet corpus. And if we had to fine tune it on a specific task, then we would take the same backbone architecture, right? We'll take its embeddings up till a particular layer and then add a classifier on top of it. Right, so that existed already in computer vision, and this transformer-based architectures started that race and started that kind of made it popular, right? Pre-training and fine-tuning. Now let's look at relatively size of the models, and the evolution of these models. So when first transformer-based architecture, Robota or BERT came in, the largest vision model was VGGNet, which was 144 million parameters, and Robota at that time itself was 355 million, right? Just double the size of that. And then came GPT-2, which again, more than double the size, more than 3 times the size, it's 1.5 billion parameters. And then we have GPT-3, which is 175 billion parameters, right? So now the question is, so here I'm showing approximate time that it takes and the resources that it takes to pre-train these networks. So for example, Robota would take 410 A100 days, right? If you were to train Robota on just a single A100, it will take 410 days. And they are alternatively, you can use 410 GPUs and train it in a single day. And GPT-3 would take 60,000 A100 days, right? So with 2,000 A100, it would take roughly a month, right? So now, if we have to take it forward and train a 1.6 trillion transformer, how would you do it? And what are the resources that it will take, right? If I simply extrapolate that, even on 2000 A100s, it will take 9 months to train such a big model, right? So is this feasible? Is this efficient? How should we go about it? How should we do this, right? So, but before we talk about it, let's quickly look at why do we even care about model size? Why do we want, what is this race about? Why do we want to increase the model size, right? So the answer there lies in the neural scaling laws. You guys will discuss and study this in a separate lecture on scaling laws, but I will just motivate a mixture of experts using this. So this graph that you see here on the x-axis, you have the number of parameters, and on the y-axis you have the loss, right? So it says that as you increase the number of parameters, your test loss is gradually decreasing, right, irrespective of the model. So here, when you are not restricted by the data size and the compute and the model size, sorry, data size and the compute, right, you are increasing the model size and you are using whatever resources it takes to train that model efficiently, whatever model size that it takes, using those many compute and whatever training data that it takes, right? So this is the reason that we worry about increasing the model size, because empirically we have seen that increasing the model size improves the performance, monotonically reduces the graph, right? So these we have similar curves when we plot them with respect to the compute that we have or the data set size, keeping the other two unrestricted. And another interesting observation that this paper made is that if you have a fixed compute, then what should you choose? Should you train a smaller model for more number of iterations, or should you train a larger model for small number of iterations? Right? Again, you will discuss this. I'll just tell you the conclusion that it is more efficient to train a larger model for small number of steps given fixed compute, right? And that is why the whole community is kind of focused about increasing the model size and trying to see what is the limit, right? So, but now the question is, how do we efficiently increase the model size, right? If you just keep on going this way, we saw that it's going to take more than 9 months. So the answer lies in mixture of expert concept, which we will study today. And at a very high level, the idea is that we have a lot of parameters, but we will not activate all of them when we are using it, even neither during training nor during inference, right? So at any point in time, only a subset of all the parameters are going to be active for a given input, right? So this concept of mixture of experts is not new. It was introduced in 1991 by Jeff Hinton's group, right? And let's first look at what is the idea of mixture of experts, right, as a model. So typically, you have a neural network or any model, right? We'll call it expert, an expert in this lecture. It takes an input X and gives you an output Y, right? Now, in mixture of experts, instead of one model, we have n models or n experts. These could be simple MLPs or an SVM layer separately, right, or whatever. In addition to these, we have a gating network. Now, when an input X comes, the gating network selects which experts should be activated, right? For example, in this figure, expert 2 and expert n-1 are active. So these two experts will compute their respective outputs, y2 and yn-1, and we will multiply them with the gating probabilities, right? So g of x2 is the probability of routing to x2, and g of xn-1 is the probability of routing it to expert n-1. We multiply it with that, and adding them gives us the output, right? So this is the whole idea of mixture of experts, that we replace one expert with n experts. We add a gating network, right? The job of the gating network is to select an expert or multiple experts for an input, right? And the output is nothing but the convex sum of the individual expert outputs, right? And this is the case when all the experts are active. So this is the architecture which was introduced in 1991. Their idea was not to reduce the computation cost, but to increase the capacity of the model. So what they do is that they get an input X. This gating network computes the probability of routing to all the experts. So this G sigma X is a softmax. That means it gives you a probability of each expert getting selected, right? So you will pass the input through all of the experts, and then the output is going to be simply a convex sum of the output of different experts, right? So this mixture of expert models, so let's look at the chronology of how it progressed. First introduced in 1991. Here each expert could be even a neural network or an SVM or Gaussian mixture. And then in 2013, Eigen et al. Used MoE as a layer in deep learning, right? Then in 2021, in Google Brain, MoEs, they created switch transformer, where MoE layer was used in a transformer based large language model, right? And then came Mixtral in 2023-24, which made a lot of models public. So their most popular one was 8 x 7 billion, which had 8 experts of 7 billion sizes, right? And the good thing there is that its license is commercial friendly, which means we can also use it, and it surpasses GPT 3.5 Turbo, Claude, Gemini Pro, Llama 270 billion on many human benchmarks. So, right, so this created a buzz in the market. Now let us see how we use mixture of experts as a layer in the transformer based architecture, right? So on the left hand side, you see a normal dense transformer block. First, we have an attention layer, right? So this is the attention layer. Then we have we add which acts as a residual connection and then normalize, then pass it through the feed forward network, right? This blue block is the feed forward network, and then we again add and normalize. Now let's run through an example, a very simple example, where this input X is a sequence, more parameters. It has two tokens. First token is X1, which is more, and the second token is X2, which is parameters. We add the positional embeddings. It goes through the self-attention layer, where embedding of each token is getting, impacted by its neighborhood, right? Now we add and normalize. This is the residual connection. Now each embedding, right, embedding of both more as well as parameters will pass separately and independently through the router. This router is gonna assign probability of selecting an expert, right, for both the tokens independently, right? So for example, for the token more, it selects expert 2 with the probability 0.65. And for the token parameters, it select the expert 1 with probability 0.8, right? And then we multiply with the probabilities and then pass it through the residual network, and right, add and normalize. Again, this add and normalize is applied on each embedding independently, right? In embedding of more as well as parameters independently, and we get the corresponding embeddings y1 and y2, right? And how are we reducing the computational cost here? We are reducing the computational cost because for an embedding, for an input token, only one of the 4 experts are active, right? So the computational cost is exactly same as what we have in the dense, except for the router part, which is negligible anyway, right? So what is the increase in the computation cost? It is the routing to the, it's essentially passing through a linear layer and doing a softmax for the number of, for each token, right? So this block is MoE layer, and on the left we have a dense transformer block, and on the right we call it as sparsely activated mixture of expert transformer block. So the question is that why is training faster using MoEs? What is happening underneath, right? So I think this is a fundamental question. What is happening underneath? Earlier, when mixture of experts were introduced, right, they were not introduced for speeding up the training. They were introduced to increase the model capacity size. They wanted to increase the model capacity, right? So therefore, they created n experts, and at the input level itself, at the initial layer itself, the router would choose to which model should it go, right? Here, training is not becoming efficient at all, right? However, when we are using mixture of expert as a layer, so this again on the left hand side here, this is one transformer block, right? The entire model will have multiple such blocks, right? In general, 32 blocks, right? So this is first, and the input sequence will come from here. This is the input sequence, more parameters, right? This is the input sequence that is coming here. This routing earlier was happening at the input level. The entire input more parameters would go either to one model or to the other model, one expert or the other expert. This can happen at the token level as well in one input, right? Who says that we need to do it at the sequence level? We can do it at the token level as well, right? So that is what is happening here. We have, let's say, 10,000 tokens in a batch, right? And we have 100 experts, right? It may happen that, if there's a uniform distribution, then, each expert will get 100 tokens only, right? Which expert will get which token? That depends on the router, right? And that assignment can be different in different layers, right? So in each of this layer, we have a feed forward layer, right? We are replacing this feed forward layer with this mixture of expert, right? In first layer, this token more got assigned to feed forward layer 2. In the next layer, it may get assigned to fourth expert, right? So this token more, this may get assigned here, right? So the key idea is using it as a layer in a deep network and stack it on top of each other. Does that make sense? Right? And why are the number of parameters increasing? Because 80% of the parameters in a transformer architecture lie in feed-forward network. Attention layers correspond to only 20% of the parameters, and we are scaling that up. If we have 8 experts, that we have increased the model size by 8, roughly, right? And why is training efficient, right? Because let's say each feed-forward layer is hypothetically 1 million parameters, right? We have increased the number of parameters to 8 million, right? But only one of them is active at any point in time, right? So the number of computations that are happening is only 1 matrix multiplication, not 8 matrix multiplication for an input, right? So that's what is giving it efficiency. That is called conditional activation of an expert, right? Now let's quickly see how the backpropagation work in mixture of experts, right? And for that, for a moment, let's go back to the dense model, right? Here all the experts are active. So this gating network will give us the distribution probability for each token. For a token X, we will have the distribution probability, right? Probability of selecting an expert. Output Y for a given token is going to be convex sum of the output of each expert, right? And so we are calling each of this this output as Yi, right? And to see how backpropagation works, let's look at the computational graph, right? So here Y is the output and for each token, and it is computed as the sum of the output from each expert, right? So Yi here is nothing but G of Xi into E of Xi, right? Gxi is the probability of selecting the ith expert, and Ei of X is the output of expert I, right? And when we backpropagate, we will get the derivative of the loss with respect to the output Y from the layer above it, right? This will get passed on to each of the experts output, right? Yi's. So derivative of the loss with respect to each expert Yi is exactly same, right? You can see from this equation, right? So if you apply chain rule to this Y equal to this, you will get derivative of loss with respect to each of this Yi is derivative of loss with respect to Y into derivative of Y with respect to Yi, which is, this is 1, right? Simple chain rule gives us that the derivative of the loss with respect to each of the expert is nothing but the derivative of the loss with respect to the output that we get from the above. And again, a simple chain rule here would give you that the derivative of the loss with respect to Ei of X, right? So here, I mean, again, we can do the chain, we can apply the chain rule, right? So Yi is G of Xi into Ei of X, and derivative of the loss with respect to Ei of X is going to be derivative of the loss with respect to Yi multiplied by the derivative of this so derivative of E of I with respect to Y, derivative of Yi with respect to E of I, sorry, right? And this is nothing but G of Xi, right? So this is a simple chain rule, and similarly for G of Xi, which is the router probability, we get the derivative of loss as expert output transpose the derivative of loss with respect to Y, right? So you can easily match the dimensions and see that this is correct, and this is nothing but simple chain rule that we have applied. This is the case when we have a dense MoE where all the experts are active, right? Now, to introduce sparsity, what we have to do, we have to greedily select an expert, and what switch transformer does is that instead of selecting all the experts, it does an argmax. It takes the expert to which maximum probability is assigned. We are calling it I star, and the output is nothing but the probability of the the maximum probability into the output of that specific expert, right? And similarly, we can get the derivatives with using the chain rule here, right? And all the other derivatives are zero, right? So this speeds up the back propagation as well, right? Other than I star, which is the maximum, which is the expert which got the maximum probability, everything else is zero. All the derivatives are zero, right? So this introduces sparsity, right? This specific sparse mixture of expert was used in switch transformers. And there are other ways as well of introducing sparsity. So for example, one of them is noisy top K gating. This was introduced by Norm Schisser in in an MoE architecture, which was using LSTMs, which came before switch transformers. And there they chose two experts instead of one. How does noisy top K gating works? So h of xi here is the logic that we get from the gating router, right? And earlier we had g of x, which was the routing probability, which we obtained by doing a softmax over these logics, right? So now they introduce some noise on the logics, right? And the amount of noise is also controlled and learnable, right? So this is a learnable parameter which we had earlier as well, and they introduce another learnable parameter for the noise, to control the amount of noise, which is W noise here, and this is kind of predicting the standard deviation in some sense. And standard deviation has to be always positive, therefore we pass it through soft plus activation, which is nothing but a smoother version of ReLU, right? So this ensures that the standard deviation is always positive. And now the question is, why do we add this noise? Well, we will not go into the details here, but they claim that this improves the learnability and makes the learning more stable of the mixture of experts, right? Maybe we can cover this in tomorrow's lecture, but for now we will hold it here, right? And then they have a keep top K operator, which is just selecting top K logics and putting everything else to minus infinity. This minus infinity will ensure that once you do a soft max, it will get zero probabilities, right? So we compute the logics for an input. So the way it works is that we compute the logics h of x, which is noisy. There are two parameters there, one for the mean, the other for the noise. We pass it through top K, which ensures that only K are active, others are set to minus infinity. And then we do a soft max over this. So right, so this gives us a sparse MoE layer. If we select, let's say, K equal to 2, then we have only 2 active experts, right? So yeah. Now we have looked at how mixture of experts work in this in deep learning and in transformers. Let's try to do some analysis on top of it, and let's see what is actually happening underneath. How is the learning progressing and all of that, right? So one question is that why do these experts not collapse in practice? Why do you think that these experts? Okay, so now let us see. So there are some practical considerations when we are training MoEs, right? So one question is that why should these experts not collapse, right? I mean, you're training it through backpropagation. All of the experts have been initialized using the same scheme randomly though, right? They are trained using the same optimizer. It is possible that all of them will learn the same weights. How will you ensure that they are learning different weights, right? So there is a work which is towards understanding the mixture of expert layer in deep learning. They analyze this question, and to answer this, they consider a synthetic setup. They create data synthetically. Now, what they do is that they create data in this fashion. So there are 4 clusters, and these are the 4 clusters, and each cluster is linearly separable, right? So this can be separated using this. So you can have one expert. Ideally, what should happen? That any data point which is coming from this cluster should get assigned to this expert, right? And this linear classifier expert should be able to distinguish between the positives and the negatives, right? So these are the positives and these are the negatives, right? And if a data point is coming from this cluster, then router should assign it to this expert corresponding to this cluster, and then a linear classifier. So this is in high dimension. This is linear in high dimension, right? This is a two-dimensional representation, right? So it will get assigned to this cluster, and similarly, if a sample is coming from this cluster, it should get assigned to this expert, which should be able to classify it linearly, and similarly for this, right? Now, this is the data that they create synthetically, and they train they create a mixture of expert model. And first, they consider mixture of linear experts. Now, this is how it gets initialized. Here, color of the dot is telling you the expert to which that data point got assigned, right? And the lines are the boundary curves learned by 4 experts. And when they trained this, they found that first, the router has not learned meaningfully, right? For example, in this cluster, you see that this green expert is also getting routed here, right? And blue as well and red as well, right? So it has not learned properly. On the other hand, when they changed their expert to a non-linear expert, they introduced some non-linearity on top of the linear layer. What they observe is very interesting, which is that there is a clear separation, right? The router has learned perfectly. Each data point is getting assigned to the right expert, right? So what is happening here, right? So they prove theoretically as well that non-linearity here is essential. What is happening is that if you have a linear layer, your loss function becomes convex, and all the experts, even though they initialize from different random points, they all converge to the same minima or similar minima, right? On the other hand, if you have non-linearity, then even if you start from similar points, right, even if experts are initialized in a similar fashion, non-linearity kind of ensures that they diverge to different points in the space, right? So this was an interesting experiment, and then they go on to study the learning dynamics of the expert and the router, right? So what happens? What do you think? What will get trained first? Will the expert get trained first, and then the router will learn to assign each data point to the appropriate expert? Or do you think that first the router will learn, once the data points have been assigned correctly to each of the experts, then the corresponding expert will start to train and will learn the classifier boundary, right? So what happens when you train this, right? And they show empirically that learning of MoEs happen in 2 stages. One, first is the exploration stage, right, where router is nearly untrained. It randomly assigns data points to each of the experts, and the experts start to diverge, right? So each expert will go to different points in the parameter space, and once that happens, when each expert is getting a different, is at a different space, then router starts to learn, right? And how do they quantify and how do they see whether the router is routing to the right expert, right? So for that they use the notion of entropy, right? At a very intuitive level, entropy quantifies the amount of randomness. So if a router is assigning equal probability to all the experts, then the entropy is going to be very high. Whereas if the router is routing to only one expert, one data point, then entropy is going to be low, right? So they use the data statistics of which sample is getting routed to which expert, and they know a priori the cluster from which it belongs, right? Remember that it's a synthetic setup, right? And this is how they define entropy. And when they plot entropy with respect to the training epochs, they see that initially, here entropy is quite high, meaning that the router is routing equally to all the experts, right? It randomly, it's assigning almost equal probabilities to all the experts for a given token, and then as the learning progresses, the entropy reduces. This reduction in the entropy essentially demonstrates that now the router is routing a given sample to only one of the expert, right? So we discussed about the architecture of mixture of experts, how does the backpropagation works, and we also looked at some theoretical analysis of what is happening beneath, why are the experts not collapsing, and how the learning of the router and the experts going on, right? So now, and we, of course, there are certain pros of a mixture of expert layer, and that's why we are studying it, right? So we wanted to increase the number of parameters efficiently. That is one plus point that we get, right? We are able to increase the model parameters, but thanks to the conditional activation, we are able to keep the compute restricted, right? We have efficient pre-training due to conditional or sparse computations, and similarly, because of sparse computation, inference is also quick, is also fast, right? But then there are certain issues as well that we need to handle, right? So the first and the foremost issue is the unstable training of experts, right? In practice, many a times we see that a random run, can result in the divergence of the loss. So, for example, this is a graph from one of the papers where on the left-hand side you see a training run which diverges, right? Training loss suddenly spikes up in the left curve, and on the right we are training the same architecture. Difference is random initialization, and here we see that it is converging, right? So designing a stable mixture training, right, for mixture of experts is very crucial, and that's where the innovation lies. That's why it took from 1991 till now to make them useful, right? And these are the tricks of the trade that we will discuss maybe in the next lecture, right? We'll go through various papers and we will see what are the nuances and that those guys have introduced, right? So, and another issue that can happen because of which we may have unstable training is the router collapse, right? What if, so earlier we saw why experts are not collapsing, right? Nonlinearity is helping there. Now, what if the router collapses? Meaning that the function, that the linear function which it is learning, it routes all the tokens to only one expert, right? Then we have a very big network where, let's say we have 8 experts, then we have 8 times the size of the network, but 7 of them are useless. They're just sitting idle. They're never getting activated, right? So that's useless. So how do we take care of router collapse, right? So this is again something which we will look at in the next lecture. There are a lot of modifications to the loss functions that we do to avoid this router collapse. And then another issue is that of very high memory requirement, right? We saw that this conditional activation is able to reduce the number of flops that we are doing, right? But still we need to keep all the experts in the memory, right? We can't keep them off the GPU and load them only when the router routes to a particular expert, right? So we need to keep them all in the memory, right? So even though we have been able to make the compute efficient, memory requirements, GPU memory requirements still remains very high, right? And of course, I don't think that there is any other alternative to that. What we can do is we will also discuss this in the lecture tomorrow, that what are the efficient ways of doing that. If you have multiple GPUs, how do you shard a particular model or expert layers on different GPUs and ensure that you are able to load such a big model and train it as well, right? So I think that's it for today. Tomorrow we will go through various papers and we will see what different what are the different tricks of the trade that makes MoEs usable. Right. So that's it. Thank you.